In this video, we work another problem involving exponential functions. It's exercise 101 from section 5.5. It says a lake is stocked with 500 fish and the population increases according to the logistic function below. Here t is measured in months. So this is the function y equals 10,000 divided by 1 plus 19 times e to the negative t divided by 5. And this is what the graph looks like. But we're really only interested in the part of the graph for t greater than or equal to 0. So this is our population graph. And then if we evaluate that at t equals 0, we see that at t equals 0, we've got 500 fish, and then the number of fish in the pond increase. And as t goes to infinity, it looks like the values approach 10,000. And I think that that makes sense. So that's actually our first question. The question says, what is the limiting size of the fish population? And I think we can see that it's 10,000. Let's actually work that out on paper first. So it's relatively easy to compute. We're just letting t go to infinity. And we've got an exponential term in our equation, or excuse me, in our function. We've got e to the negative t divided by 5. If t is a really large number, this is going to be a really large negative number divided by 5. So it's still a large negative number. So whenever we have e to a large negative power, that expression is going to go to 0 as the exponent goes to negative infinity. One way that you can see that is if you just graph y equals e to the t. As t goes to negative infinity, the y values on the graph approach the y-axis. You can also imagine substituting in, say, like negative 10,000 for t. Well, you could take negative 10,000 and divide by 5 if you want to, and you still get negative 2,000. Still a relatively large exponent as far as the magnitude is concerned, but it's a negative. Now, any number raised to a negative power can be rewritten as it's 1 divided by itself, raised to the same power but positive. So this is 1 divided by e to the 2,000. That is a huge number. So 1 divided by this very large number is going to be a very small number. So this exponential expression is giving us a very tiny positive number. And as this t gets larger and larger in magnitude, this numerator is going to get larger in magnitude, but increasingly negative. And so what that's going to do for us is it's just going to add zeros to this exponent in the denominator. So the denominator is going to get larger and larger, which means the fraction is going to get smaller and smaller. And as that happens, this guy goes to 0 in general, just like this function approaches 0 as t goes to negative infinity. Since that's true, this goes to 0, and we just end up with 10,000 divided by 1, which is 10,000. Since the limit as t goes to infinity of our function is 10,000, that means that y equals 10,000 is a horizontal asymptote of the function, or the graph of the function. I'm actually not sure if I should call it the graph of the function or the function itself. And again, what does that mean for us? That means the population is approaching 10,000 fish as t goes to infinity. So we started with 500 fish, and then sometime in the future, the fish population in that pond or lake or whatever it is going to get closer and closer to 10,000. So we can plot that horizontal line. We see that the graph gets closer and closer to that line as t goes to infinity. Looks roughly like that. And it looks like around t equals 40, it's almost the curve itself and the horizontal line are just like almost identical. So it looks like all the interesting things happen between t equals 0 and t equals 40, and then it just sort of flattens out. Now part C asks us, this is part B. I wonder what part A was. Oh, part A was just to graph the function, and we did. Part B was to find that limiting size of the population, and part C says at what rates are the fish population at what rate is the fish population changing at the end of 1 month and at the end of 10 months? And t is time in months, not years. Forgot about that. So we just want that instantaneous rate of change of the fish population at t equals 1 and t equals 10. So we'll compute the derivative. And then after we compute the derivative, we'll plug in t equals 1 and t equals 10, and then we'll see what we get, and we'll interpret those numbers in terms of populations of fish per month, or numbers of fish per month. That was actually part B. So part C asks us for rates of change. So we're taking the derivative with respect to t of p. And our equation for that population of fish in the lake as a function of time is this equation. Now, since 10,000 is just a constant in the numerator, this derivative is actually easier to evaluate if we think of all of this in the denominator as itself raised to the first, and then bring that up to the numerator. So we're going to have this number times this base raised to the -1 instead of the +1. Then when we take the derivative, we'll just use the power rule rather than using the quotient rule. We could use the quotient rule. Since that numerator is just a constant, it's easier to use the power rule. All right. So I'm using the power rule and the chain rule. I've got the derivative of a constant times a function raised to a power. That function is our inside function. Now, according to the chain rule, we take the derivative of the outside function first. So it's going to be 10,000 times -1 times the original inside function to the -1 minus 1. -1 minus 1 is -2. You put the inside function back inside, don't change it, just plug it back in. And then you multiply by the derivative of the inside by the chain rule. Now the inside function has two terms. Derivative of 1 is just a 0, so you're gonna have 0 plus the derivative of this guy. Yeah. Derivative of this also requires the chain rule because we don't just have a t inside the exponential, we've got a -t divided by 5. So we'll say, what's the derivative of 19 times an exponential? Well, according to the chain rule, we get 19 times the exponential evaluated at the inside function times the derivative of the inside. Now you could use the quotient rule there, but again, we've got a constant in that denominator, so it's easier to just write it as a constant times t. -t divided by 5 is the same as -1/5 of t. So you can think of that t as t over 1. T over 1 times -1 over 5 is -t divided by 5. So that is equivalent to that. Now I've got the derivative with respect to t of a constant times t, and that's just this constant, -1/5. And you're multiplying, so make sure you put that in parentheses. Without the parentheses, it looks like you're subtracting 1/5, and that's not what we want. So dp dt is this -10,000 times this exponential, form, raised to the -2. So we can put that in the denominator and make that a +2. Times this 19 times that -1/5. If you want to, you can say -1/5 of this is positive 2,000, right? So we'll have 2,000 times 19 there. And then we've got the exponential. We'll leave that alone. And this can be written in the denominator if we change that exponent from negative to positive. One thing we notice right away is that exponentials are always positive. So this is a positive number, and this is a positive number plus 1, and then we square it. So the denominator is definitely positive. This is positive, and then the 2,000 times 19 is 38,000. So this rate of change is always positive, which just means that population is always increasing. So every month we're adding new fish to the population. I guess they're reproducing. So they're reproducing all the time, and this is the rate at which fish are added to that population. Now, I think they asked for the rate of change of the population at a couple of different values of t. I don't remember what those are, so I'll check that out, and then we'll evaluate this function at those values of t. So this is our p prime. We see have a little relative max at 14.72219. So about 14.7 months from the time those 500 fish were released into the lake. That rate of change is at a maximum. But we see that the rate of change is always positive. Now they asked us for the rate of change at the end of 1 month and at the end of 10 months. So we can just compute P prime at t equals 1, and we get this value. And we can evaluate the function there. We can plot that point. We can also evaluate the derivative there and plot that point. If we zoom in, we can see a little bit better what's going on there. So the orange graph is their original function. So this is just saying 1 month after those 500 fish were released into the lake, there are 604 fish. And the population of fish is increasing at a rate of 113.5 or approximately 114 fish per month. So as we go from our first month to our second month, we're expecting to add about 114 additional fish to that 604 fish that are already there. Now we can also find the rate of change at 10 months. So we'll just plug in t equals 10 to our p prime. I'm at 403. So that means after 10 months, the fish population is increasing at a rate of 403 fish per month. Now at 10 months, there are already 2,800 fish in the population. So we've got 2,800 fish in this lake, and every month we're adding 403 new fish, or at least at that moment at t equals 10 months, we're adding an average of 403 fish per month. So that's our rate of change, and that's coming from the derivative function. You might say, okay, it looks like the fish population is just exploding. It's increasing exponentially. Where is it going to stop? Where is it going to sort of slow down? We know that the population is going to continue to increase, but when is it going to stop increasing as fast as it's increasing? Or when is the rate of increase going to max out? Well, in order to do that, in order to find that, we can find the maximum value of P prime, or alternatively, we can think about finding the point of inflection of this curve. That's actually the answer to part C. Part C says, after how many months is the population increasing most rapidly? Well, one way that we can explore that is to just look at the tangent line. I like to graph tangent lines, you know I do. So there is just a point on the curve. Let's start with t equals 1. And then let's graph the tangent line there. Now, if we graph this tangent line and let t naught increase, we see that at t naught equals 1, the slope is, what is it? 113.5. Now, as our t values continue to increase, we can see that the tangent line is getting steeper and steeper. And it gets to its sort of steepest point at that 14.7 number, that maximum of the derivative function. It's a little bit easier to see if we ask Desmos to stop labeling all those points. So sometime around that 14.7 mark, 14.7 months after the 500 fish were released into the lake, our tangent line is as steep as it's going to get. And then after that, it still has a positive slope, but it starts to flatten out a bit. The rate of increase starts to decrease, if that makes sense. Or in other words, the derivative is decreasing, even though the derivative itself is positive the whole time. And so our maximum seems to be at about 14.7, which is the same as the maximum on this curve, 14.72219. Now we can find that analytically if we compute the second derivative, set that equal to 0, and then solve for t. So let's do that and see if we can't find an exact answer as opposed to just reading a graph and getting a decimal approximation. Okay, so again, we have options. We know that this is our P of t, or P prime of t, excuse me. And we want to find the maximum of that P prime. We're looking for the number of months, that's a t value, when the population is increasing most rapidly. So when is this P prime at a maximum, essentially? We can find the values when that function is at a maximum by rewriting it. I might write this as 3,800 or 38,000, sorry. Is that right? Yes, I think it is. Divided by, if I wanted to, I could write this exponential in the denominator, e to the t divided by 5 times 1 plus 19 times e to the negative t divided by 5 quantity squared. Now that's p prime. Now we know this is positive, we know this is positive, and we know this is positive. It's like looking for it to change signs. I don't know if we're going to be able to find a place where it changes signs. Are there any t values? Might think about having any t values where the function is undefined. I think the function is going to be well defined for all t as well. This exponential is always positive. We multiply it by 19, so it's still positive. Then we add 1, so it's still positive. So this is always, yeah, I think we're going to have to compute the second derivative. So let's do the second derivative of p with respect to t. So we have the derivative of 38,000 e to the negative t divided by 5, all divided by 1 plus 19 e to the negative t divided by 5 quantity squared. Now to compute this, we need to apply the quotient rule. So we know that the derivative of a quotient is the bottom function. So it's low d high. It's the bottom function times the derivative of the top function. Now the derivative of the top function in this case is 3,800 or 38,000, sorry, times the derivative of e to some power, which is e to that power, times the derivative of the inside, and the derivative of negative 1/5 t is negative 1/5. So I'll have that there. That's low d high minus high d low. And I actually am running out of space. I'm just going to write high d low here. All divided by low, which is this. We're taking something squared and we're squaring it again, so it's going to be raising it to the 4th. So this is that's the plan, but I actually have to write out that top function and the derivative of the bottom function here, and then hopefully we'll be able to factor it and set p double prime equal to 0 and solve for t. So we have p double prime of t is this low d high minus high, so that's our top function, d low. Now the bottom function is this function squared. The derivative of a function squared is just 2 times the original function. We put the original function back inside, and then you multiply by the derivative of the inside by the chain rule. The derivative of 1 is 0. The derivative of 19 times an exponential is 19 times the exponential times the derivative of the inside of the exponential, which in this case is negative 1/5. So you've got all of that divided by 1 plus 19 e to the negative t over 5 quantity squared. Oh, wait, quantity to the 4th, because we squared it and then we squared it again to get p double. All right, so now we're looking for common factors so we can factor out of everything. I see I've got a 3,800 or 38,000 here and here. I've got an exponential term there and there. I also have that negative 1/5 there and there. And I have this 1 plus 19 e to the negative t divided by 5. Whoops. So if I'm looking at this expression and I'm looking at this expression, I'm saying, what do they have in common? Well, they have one of those 1 plus 19s, e to the negative t divided by 5. They've got one of those 3,800s, or I keep saying 3,800, 38,000 times the negative 1/5 times the exponential. And I think that's it. I think that's all I can factor out from both of those. And then I open some parentheses and I say, this times what will give me this expression? Well, I factored this out, I factored this out, I factored this out, I factored out one of these, so I still have one of those remaining. So I'll have 1 plus 19 times e to the negative t over 5 inside these parentheses here. And then I say to myself, okay, this times what will give me this? Well, I need the negative. I've already taken care of the 38,000. I've already taken care of the exponential. I haven't taken care of the 2, so I'll put the 2 down. I already factored that out, so that's gone. The 19 is still there. The exponential we factored out and the -1/5 we factored out. So we've got that there. And we're taking all of that and dividing by 1 plus 19 times our exponential to the 4th. Now I've got that expression to the first divided by that expression to the 4th. So one of those will reduce, and I'll just have 3 left in the denominator. And then this actually does simplify. This is 1 minus 2 times 19, which is 38. So I have 1 minus 38, which is -37. So we're going to have 38,000 times -1/5 times the exponential. And then we have 19 e to the negative t divided by 5 minus 37, all divided by this exponential expression cubed. And then the question becomes, well, when is p double prime equal to 0? Well, this constant's never 0. This constant's never 0. Exponentials are always positive. And this is an exponential times 19, so it's still positive. Then we add 1 to it, so it's positive. Then you take this positive number and you cube it, and it's still positive. So all of these terms are either positive all the time, negative all the time, or positive all the time, or positive all the time. The only one that potentially changes signs or is potentially even 0 is this expression here, because I've got an exponential which is positive and I'm subtracting 37. Well, that could be 0 whenever this expression here is equal to 37. So if I'm setting p double prime equal to 0 and solving for x, or solving for t, excuse me, the only term here, or the only expression that could possibly be 0 is this one. So we'll say that equals 0 if 19 times the exponential minus 37 is equal to 0. And I want to solve for my exponential function, so I will add that 37 to both sides. And then we'll divide both sides by 19. And then we will take the logarithm of both sides. And the logarithm of the exponential just gives us that -1/5 of t. And we'll multiply both sides by -5. And that will give us a t value that is equal to -5 times natural log of 37 divided by 19. I feel like I must have made a mistake. Because this is going to be greater than 1, and then I'm multiplying by -5. That doesn't seem right. So it looks like I made an error, an algebra error. When I computed the second derivative, I have a maximum right here, and that can't be right. I think I see what I did wrong on my paper. So I'm going to go back to the paper and then revise this answer. I did use the Desmos calculator to get that 38,000 times -1/5 of the -7,600. So let's go back to the paper now. We got this. I factored out this, I factored out this and this and this. And I said, okay, what do I have to multiply this by to get this expression? I've taken care of that part, and that part. I've taken care of one of those, so I'm left with one of those. Now here, I factored out the 38,000, the exponential, the -1/5 on the far right, and then I have one of those 1 plus 19 e to the negative t divided by 5. Okay, so what is left? I said there's just a 2 and a 19, but I think I assumed that I already took care of the exponential, but I actually had 2 of those. I had that exponential from the top function and then the derivative of the inside from the derivative of the bottom function by the chain rule. So I only factored out one of those, so I need to have another one of those right here. So this is actually a -2 times 19 times the exponential. And again, this factor here is the only factor that is potentially zero. After we simplify, this is non-zero, that is non-zero, that is non-zero because it's exponential, which is always positive. This is a positive exponential expression cubed. So the only thing that might be zero is this, but it's not simplified. This is 19 minus e to the, or times e to the negative t divided by 5 minus 38 of the same thing. So that's actually going to give us a negative 19 minus 2 times 19 of those is going to give us negative 1 times 19 of those. And then we'll just have the 1. So I don't have the 1 minus the 37 or the 38 anymore to give us a 37. We're just going to have a positive 1 there. So again, the only way that this expression is zero is if this expression in parentheses is 0. My expression was wrong though, because I forgot that exponential factor. So if we correct that, we've got a negative 19 e to the negative t divided by 5. This is plus 1 equals 0. And this is going to be much better. We made a mistake here because we had the wrong number there. Now, if I'm trying to get the exponential by itself, I'm going to add 19 times the exponential to both sides. And now I see a bunch of positive numbers, and I'm much happier about that. When I divide both sides by 19, I get 1/19. And then if I want to get rid of the exponential, I take the log of both sides. So I have log of 1/19 equals log of the exponential e to the negative t divided by 5. Now this natural log and the exponential with the same base undo each other. And we end up with negative 1/5 of t equals negative or equals natural log of 1/19. And if you're saying to yourself, oh, you're still going to get a negative answer, we're actually not, remember, because whenever we look at a logarithmic function, that logarithmic function is negative on the interval from 0 to 1. Since I've got log of 1/19, that's going to be a negative number, and I'm going to multiply it by a negative 1 or negative 5 to get the t by itself. So if I multiply both sides by negative 5 now, we have t equals negative 5 times natural log of 1/19. Or if you want, you can use that log property. Log of a over b is log of a minus log of b. And log of 1 is 0. So this is actually negative 5 times negative log of 19. The negative times the negative gives us a positive 5 times the natural log of 19. And natural log of 19 is positive, and we're multiplying by 5, so it's still positive. And that's going to give us a finite number. I bet it's that 14.7 number that we saw as the maximum of p prime. Let's see. Okay, so this is our simplified p double prime, which was incorrect because I forgot that exponential factor. The exponential should have a coefficient of negative 19, and then we're adding 1 to that. So this is actually what our exponential or our p double prime looks like. And if we zoom in, we can see that it equals 0 at 5 times natural log of 19. If you are not sure, you can evaluate. I said t sub 4 equals this value. If we evaluate p double prime at that t value, you can just substitute t sub 4. You get something that's nearly 0. Or you can evaluate at 5 natural log of 19. You get something that's nearly 0. For some reason, it's not giving us the exact, or not giving me the exact answer that I wanted. If I ask Desmos to plot that point, it gives me that 14.72219. So after that many months, the second derivative is 0. And we see that to the left of that point, the second derivative is positive, so the original graph is concave upward. And to the right of that point, the second derivative is negative, so the original graph is concave downward. So you say, okay, well, what does that mean in terms of the original function? Well, that just means that on this interval from 0 to 14.7 months, that fish population is not just increasing, it's increasing at an increasing rate. So the rate of change is positive, but the rate of change is getting increasingly positive as we go from 0 to 14.7 months. And then we say, okay, after 14.7 months, the population continues to increase, but the rate of change starts to decrease. So we're not increasing at such an increasing rate anymore. We're going past that point of inflection. And even though those slopes are all positive, they're less positive than they used to be. And that tangent line starts to sort of flatten out as we approach, or as t goes to infinity. And as the population approaches that 10,000 fish in the lake. So let's see, what should we say? What did the question say? After how many months is the population increasing most rapidly? We'll say the population is increasing most rapidly when t equals 5 natural log of 19, which is approximately 14.722 months after the 500 fish were released in the lake. What else should we say? I think that answers the question. That's a point of inflection. So that's when the population goes from increasing at an increasing rate to increasing at a decreasing rate. So that's when the graph goes from concave upward to concave downward.